All right, so here's an integral of a rational expression, and if you think about it, nothing's going to seem to work. There's going to be no u substitution. It's not going to be a natural log. It is a proper fraction, so we're going to try a partial fraction decomposition. So to do that, you have to factor the bottom into its linear factors and its irreducible quadratic factors. So this one's going to be pretty easy. X squared plus 2 is an irreducible quadratic because of the plus. If it was x squared minus 2, you could factor it into x plus root 2, x minus root 2, but it's not. So this is an irreducible quadratic. So that's where we're going to begin. We're going to determine the partial fraction decomposition here. Now, we'll start with the linear factor, x, and then it breaks down into this irreducible quadratic. So this is going to be a little bit different. For the linear factors, it breaks down so there's a constant on top of it. If you think about degree-wise, the degree of the bottom is 1. The degree of a constant is 0, so it just breaks down to a degree less. Same thing with the quadratics. This is a quadratic. Its degree is 2, so its numerator would be a linear expression. So any linear expression can be written as mx plus b, or in this case, we're going to go bx plus c. So now pretty much everything else is the same. For a normal partial fraction decomposition, we're going to multiply both sides by the common denominator. If you multiply a, the x's will cancel. So we're multiplying it by this, and you'll be left with x squared plus 2. Now for irreducible quadratics, there's going to be nothing we can do to make this term 0, so we're going to have to deal with that, but we'll get there. When you multiply this, you'll get bx plus c times x. So you could let x be 0, and that would get you to solve for a. And then you could figure out b and c after that with any value of x. But I'm going to do this a little bit differently. I'm going to multiply all this out. This is a good strategy sometimes. So I distributed the a, and then I'm going to distribute the x. So now I'm going to gather all of my like terms. So all the x squareds, all the x's, and all the constant terms. Any like terms you want to add together. So like if you had 5x squared plus 10x squared, you'd make that 15x squared, obviously. You'd add the 5 and the 10. Same thing here. Ax squared plus bx squared, you'd add the a and the b. And it'd still be x squared. So now we've expanded this whole side. And remember, this is an identity. So this has to be true for all values of x. So we have this polynomial over here is the same as this polynomial over here. Now, the only way that these polynomials could be the same thing is if their coefficients on their like terms are exactly the same. So this side has no x squared term. So I'm thinking here, I'm thinking of this as 0x squared minus 1x plus 4. So if this has a 0x squared term, that means over here the a plus b must equal 0. So I have that equation already. Now you look at the first degree term, I guess, the power of 1. Cx to the first must be the same thing as this negative 1x to the first. So we need, that means c must equal a negative 1. So we're done with that. We got c. And then this 2a must be equal to the constant term over here, which is 4. Oh, look at that. So we got a already. So 2a equals 4, which means a equals 2. All we need is b. But that's easy because we already said a plus b is 0, so b must be negative 2. So the partial fraction decomposition there went pretty nicely. So now we're going to integrate its equivalent partial fraction decomposition, which we said was a over x plus bx plus c over x squared plus 2. So plus bx plus c over x squared plus 2. So here we go. First thing I'm going to do is I'm just going to go with it. The 2 over x is going to be a natural log. Negative 2x minus 1 over x squared plus 2. I'm searching for a natural log there as well. The bottom derivative is 2x, and I have a negative 2x minus 1 up there. So that looks pretty promising, but that minus 1 is getting in the way, so I'm going to split up my fraction. Just like that. So you know you can do that. Anytime you have a fraction, you can split it up as long as you keep the denominator intact. So now if you look at this middle fraction, because the derivative of the bottom is 2x and I have a negative 2x, all I have to do is factor out that negative and I have a natural log. This fraction looks like an arctan. It's dx over a squared plus u squared. So we're in great shape here. That 2 over x, I don't know if I mentioned that, but I think it was just too easy. That's a natural log. I factor out the negative. This is a definite natural log, u prime over u. And this is just u squared plus a squared. And since u is x, du is dx, there's no constants you need to worry about. It's a straight arctan. So we're ready to go here. This turned out to be a pretty simple problem. If you consider that simple, I don't know. But we have 2 times the natural log of x minus the natural log of the absolute value, which you don't need because x squared plus 2 is positive. That's why is always positive. That's one reason why it was an irreducible quadratic. And then this is an arctan. Arctan is 1 over a times the arctan of u, which is x, over a plus c. Now, there's not much you can do. Well, we could do this. Maybe we should. If you make that natural log of x squared, now you could use properties of logs to make this natural log of x squared over x squared plus 2. And then we have minus 1 over root 2 arctan of x over root 2 plus c. So this is a nice simplified form of the answer. I did out in Wolfram Alpha. I didn't even look at the answer. They did not simplify it as far. But let's just take a quick comparison just to make sure. Boy, we did a lot of work here. So that looks pretty good. So there you have it. Thanks for watching, and I will see you next time.